So homework comments, 2. The first one is a lot of people turned in work that I'd like to see neater. The writing should be neater, but more important, the free body diagrams should be drawn. You don't have to use straight edges and stuff, but I should be able to tell what's parallel, what's perpendicular, what's in between. Okay. That's a habit that is going to, if you get in that habit now, you'll be happy as you go on to other classes and then after you're done with school. Okay, so that's, I'm going to enforce that with points. Especially figures and free body diagrams. And the second thing is vectors need to have heads. Don't just draw them as lines, because that can be one of two directions. That's incomplete information about the vector direction. Like, I saw this a few times. Okay, that doesn't do it. Because is the head here and it's pushing, or is it here and it's pulling? Okay. Any questions about that? All right. Before I keep rolling with rigid body stuff, does anyone have any questions related to the test? So remember so let me lay that out. The first test is Thursday. And the topics are vectors and more vectors. And then particle free body diagrams, particle statics, and rigid body free body diagrams. So those are the problems you need to be comfortable with for the test. Anybody have any? Yes.
For free body diagram, the homework number 1.
Mm-hmm.
So how I define the joint? Like, didn't say any hint what the joint should be like?
Do you have it with you?
Yeah.
Can I look at it? So rigid body, free body diagrams, number 1. It looks like this. There's a beam connected to the wall. There's a roller there. There's a cable. That goes over a pulley. And then there's a mass of 150 kilograms. And so this is a roller. This is a fixed joint. And so when you do the free body diagram, you're just going to follow the rules of those joints. You know, I listed out all the, yep.
Yeah, I understand the rules, but how would I assume that this is a fixed joint?
That's how fixed joints can be drawn two ways. They can be drawn like that, or they can be drawn like that.
Oh, okay.
So anytime you see that, it's a fixed joint.
And the roller would be like circle? Or?
Yeah, right. Or it can be like a disc like that, or it can be sort of like something wearing a roller skate. You see that a lot too. Two possibilities. So let me just do this problem while it's up here. The fixed joint over here, we know applies a force vector and a couple. I guess this thing probably has weight, so I'll just write that as mg. And then a roller always applies a pushing force toward the chosen body, away from the contacting body, perpendicular to the surface that it's rolling along. So I'll call that R for roller. And then a cable tension T. And so one by one, you're just going through all these contact points and then just going down the list of rules for the joint types and applying those loads where the joint is. Any other questions about that one? Okay. Any other questions about any of the problems? Yeah.
How many problems should we expect on this one?
It depends how many I do of what type, because they take different amounts of time. But I will. It's always. I always try to make it a 60-minute test. So I'm always trying to make a test that half the class will be gone after 60 minutes. And then half the class will use the last 20, 25 minutes. Okay, so I don't think you'll find it's like a real long test, you know.
Okay.
Yes. It's all based on those practice problems. So if you can do those problems, those assignment problems in these. All of the problems in these 4 sets, and if you could explain the reasoning in how you did those problems, then everything's going to look very familiar on the test, and you'll be able to do those problems. But it's not going to be the same problems as the assignment ones, so you need to. Sometimes people make the mistake of memorizing the solutions, and then they get to the test, and obviously it's different questions. So what you want to be able to do is say, like, be able to go through the steps of those assignment problems and understand at every step, okay, I know this direction is this because blah, blah, blah. I know this is negative because, you know, if you can do that, you'll be in great shape for the test. Yep.
Will the pancake tables be on the test set?
No. That is rigid body statics, so that's not going to be on there. Yes?
For the assignment, do we have to do free body diagram, and do we have also to do like the static, rigid body static?
Nope, not yet. That'll be on the next one. Any other questions? Yes? It's not going to be. That'll be next time.
But the assignment also for Thursday doesn't require, like the homework assignment, you have to do rigid body static? Or
Probably, yeah.
oh, for the homework we have to.
For the homework, probably.
Oh, okay.
I mean, I haven't. I'll go easy though on the assignment for today. I don't know. I'll think about it, but But yeah, there's going to be an assignment that I post today, and that's going to be part of the stuff that you turn in for Thursday.
Oh, okay. Will you go over a problem that use unit vector, like
Sure.
problems that we use unit vector?
Yeah, sure. I can do that. Any other questions? Yes.
All right, just to be clear, the pancake table, that is with the rigid body, correct?
Rigid body static, so that won't be on here. That's right. Yep. Okay. Yeah.
Tomorrow, do you have open?
Yeah, just from 5 to 6 tomorrow in 1324 next door.
PM?
What?
PM?
Yes. Ay, ay, ay. No. I don't even like imagining that. Any other questions before I start? So I'll do an example problem with a unit vector in it. What?
And then statics. The,
So I'm going to do a particle statics one.
yeah,
Okay.
20 pictures of that.
Yep. Let's see. So let's say that so let's say we have an incline that's at an angle of 10 degrees. That's supposed to be flat. That's better. And we have a mass of 20 kilograms. And then the mass is attached to a cable that attaches to the wall. And let's say that this distance is 2 meters. And this distance is 1 meter. So let's calculate a few things. So let's calculate first the cable tension. Second, the force vector applied to the box by the ground, and this needs to be frictionless. And then C, let's calculate the force vector applied to the box by the cable. And then fourth, let's calculate the force vector applied to the wall by the cable. The first thing we need is a free body diagram. So there's the weight. That's 20 times 9.81, 196.2. Then there's the contact with the ground. What type of contact comes from the ground? That's a frictionless contact. Yeah, it's a pushing force, so it's perpendicular to that surface toward the chosen body. I'll call that N, but you could give that any scalar variable name. And then we get to the cable. What's the type of force applied by the cable? That's a pull, so it's parallel to the cable, away from the chosen body. I'll call that T. And in order to put these, so the next step is to go to Newton's second law. In order to put these into Newton's second law, we're going to have to come up with a unit vector representing this direction, the one associated with that normal, and a unit vector associated with that cable force. And you can think of this notation as meaning that arrow is a unit vector in that direction, and then you're multiplying it by n in this case and p in that case. All right, so first, so for Newton's second law, we need to represent forces as vector components. So let's first go to the normal force. So here's the coordinate system. We have the angle, or we're going to do this based on angles. We know the angle of that incline. And so we're going to use cosine and sine for this unit vector. And the way I'm going to do it is I know that it's 10 degrees from a vector pointing this direction to a vector pointing that direction. So in this coordinate system, I'm going to draw a vector this way. And we know this is 10 degrees. Question? And then we know that it's 90 degrees to get from this to the vector that we want. And so I'm going to come up with an angle that represents this one, and then I'm going to go negative 90 degrees, clockwise 90 degrees to get to that. So you can think of it as positive 180 minus 10, so now we're at 170 at the red vector. And then minus another 90 gives us 80.
Question.
Yep.
Why, like, I know that normal, there's 10 degrees angles, but why we did like a non-perpendicular to the line that is going like this?
It is perpendicular to that incline. That's what we want.
Oh, the normal is perpendicular.
Yeah.
Oh, okay.
So I did this first because I wanted to get there just based on all angles that we know, you know. So first we know that it's 10 degrees to get from the negative x-axis to that vector oriented with the incline, because that's what's given directly. And then from there, I want to go perpendicular, so 90 degrees clockwise to get to the vector that we want. So theta is equal to 170 minus 90. So we're at 80 degrees. And so that force vector, the vector components for that normal force are the normal times cosine and sine of 80. Which is 0.174 n, 0.985 n. Any questions about that one? And now we have to calculate, we have to do the same thing for the cable force. This time we're not given an angle. We're kind of given components, but we have to deal with the signs ourselves. So we know that full cable, we can think of like a vector u that's in the direction of the force. Is 2 in the negative x direction, 1 in the positive y direction. So negative 2, 1. Any questions about the reasoning on that one? That's not a unit vector, though. So now we have to calculate a unit vector in that direction. The magnitude of this vector is square root of 5. And so a unit vector in that direction is negative 2 over square root of 5, 1 over square root of 5. And so then the force vector applied by the cable to the box is just the tension T times this unit vector. So I don't have a calculator on me. Can someone give me decimals for these? Okay, and then that's 0.447 multiplied by T. Yep.
Could you also do something similar to the first one by taking the two known components, taking the tangents
Yes.
of those to find the angle, then subtracting that from 180 to find the angle?
Yes, you could do that. In 2 dimensions, you can do that. In 3 dimensions, you won't want to do that. So you should get comfortable with this approach too. But yes, that would work perfectly well.
Okay.
Hi.
So basically, for the unit vector equation, we use it only when we don't know the angle, and we know the component. We know like where it's going to in the x1 and the y, or any x and y direction. We use unit vector. But when we know the angle, we just use the unit vector. We don't have to use the equation. We just apply cosine of the angle.
Yeah, so cosine and sine give you a unit vector. So if you know the angle, yeah, if you're doing it based on angles, you're always going to be using cosine and sine. And if you're doing it based on coordinates or components, then you're going to use the one where you find the vector, figure out the length, divide by the length.
Oh, okay.
So that's the difference. It's always going to be cosine and sine if you know the angle. It's always going to be this approach if you know the.
There's like two ways to calculate.
That's right.
the vector.
Yes.
Unit vector.
Exactly.
Oh, okay.
Yep.
If we aren't told whether a situation is frictionless or friction contact, are we supposed to assume it's frictionless?
You won't have to ever assume that.
Okay.
I.
Because I remember there being a few on the homework where it didn't explicitly say it.
Okay, it should have. And on a test, if that ever comes up, then come ask me and I'll write it on the board.
Also, will we be given a coordinate system or told to make one?
It could be either way. On this one, for this test, you can just use a horizontal, vertical coordinate system all the time.
Okay.
Later.
More placement of it, but
Oh, the origin, that's your choice.
okay.
I guess there could be times I would explicitly say it, but if I don't say it, then you can choose. Is there another question? Yep.
I can't tell if I'm just making this up, but it seems like if you have a tension and you have a normal force, you're going to have to use the unit vector to determine what goes.
Yes,
Okay.
that's right. So remember that we talked about two types of forces that come up in free body diagrams. Forces where you know the direction and forces where you don't. If you don't know the direction, then you just have both components as variables. If you do know the direction, then you have a scalar and a unit vector, a scalar and an arrow, right? Anytime you draw that arrow in a free body diagram, you're going to need to use unit vectors.
So like the N in an arrow or the T in an arrow is always.
Yep, that's right.
Also,
What's the keenness from using like the inverse tangent to find the angle and then instead of using a unit vector? I mean, I can see how a unit vector would be useful in like 3D,
Right.
but like if we're working with 2D, would we get marked off for not using a unit vector?
In 2D?
Yeah.
No. But in 3D, you won't want to mess with that. Yeah. Yeah, that's perfectly fine. Tangent would be fine.
So basically, for the use of the unit vector, to know how when we know that we're gonna use it, it should give like that we know the it's basically giving direction, and we don't. I mean, giving direction. And we
Yeah,
don't
think of, yeah.
like
It's giving the direction, and the thing the scalar you're multiplying it by is giving the length.
oh, okay. And
So you're breaking up a vector into just a pure length and a pure direction. That's what you're doing when you use a unit vector.
Yeah. So when we have direction, but we don't have the magnitude, we use the
You need a unit vector, exactly.
find the magnitude.
Exactly.
Okay.
Yep. Is there another question? Yep.
Can we keep asking you questions about the stuff? If we don't, we'll just work on stuff that's like after the exam?
Yes.
Okay, so we can just use this time to just ask you which question?
Sure.
Okay.
But let me finish this problem. Okay, so now we're ready to go to Newton's second law. We have these three forces. So the weight is 0, negative 196.2. The cable force is negative 0.894 T, positive 0.447 T. The normal force is 0.174 N, 0.985 N. And those have to add up to 0 because it's an equilibrium. And so we get a first equation that says negative 0.894 T plus 0.174 N is equal to 0. And the second equation says 0.447t plus 0.985n is equal to 196.2. This is a small system, so you could do this by substitution, but you can always do it by reduced row echelon form. So here's equation 1, equation 2. I'll choose the order t, n, and then those are the constants. So the first equation says t's we have negative 0.894, n's we have 0.174, constant 0. The second equation says 0.447 t's, n's we have 0.985, constant 196.2. And can someone tell me what you get if you use reduced row echelon form there?
T is equal to 35.62.
Okay.
And N is equal to
183.02. Okay. Are we done? 9! So, depending on what questions were asked, sometimes we would be done, but that's not what was asked. Oh, well, we're done with part A. It did ask for the cable tension. So the value for T is the cable tension. So A, the tension is equal to 35.62. But for B, we're asked for the force vector applied to the box by the ground. That means that, so this right here is the force applied to the box by the ground. We just didn't have numbers for it yet because we didn't know what N was. But now you can plug N in there. Can someone multiply this out with, now that we know that N is 183.02? Okay, wait. Okay, 31.78.
and then
180.24. And that is the force on the box by the ground. Oh, I didn't point out one thing that is always worth keeping in mind. We're dealing with a cable tension and a normal force. Are there any reason that we should know what the signs are of those values, T and N? Sometimes we do, sometimes we don't. Well, think about, what if you had a negative value? That would be saying that the cable was pushing this way on the box. Is that possible? No, so that T has to be positive. And we got a positive T, so that's a good sign. What about this N? If we got a negative value for N, that would say that that the ground was pulling down on the box. Is that possible? No, so it's a good thing that we got that positive N. So those are two things that give us more confidence in our answer. Okay, part C. Now we're looking for the force applied to the box by the cable. Well, that is this one. Could someone multiply 35.62 into this vector? Okay.
negative 31.86.
Okay.
15.93.
And then the last one was the force vector on the wall by the cable. In general, you have to do that by multiplying, like, we know that everywhere along this cable, that cable's applying a magnitude of a force equal to the tension that we calculated. In general, we have to use a unit vector then to figure out the direction. But in this case, we know that the force vector applied to the wall is just equal and opposite to the force vector applied to the box. So, based on that, we can just take the opposite of this, and it's just going to be positive 31.86, negative 15.93. Yep.
On this, like on the exam, would we need to like jot down, like we know this by Newton's third law or something like that, or like equal and opposites or something? Would we need to?
No, you don't have to do anything like that.
For part B and C, when we ask for cable tension, it's just because we break them on the vector because force vector, so we find the value of the unit vector times what we have.
Mm-hmm. Right. That's right.
What is when they ask for vector, we do that, but find because we need to find unit vector and.
Yep, that's right. And remember that if it's asking for the force on the thing that you isolated, you know, we isolated the box. That was what we did our free body diagram of. So if it's asking for the force on the box by anything, remember that that vector is all, you've already done the work of figuring out what that vector is for Newton's second law. Those already appear here. You just have to multiply in the scalar value that you've solved for.
So basically, first we have direction for normal and tension force. So we find the scalar value of the tension at normal by doing the unit vector, left and correct, and then after that we when they ask about the vector applied, we multiply it by the value of the unit vector.
Right.
Okay.
Yep, exactly.
Thank you.
Yes?
And the scalar multiple that we find in Newton's second law, that's the same as the magnitude of the vector?
Yes,
Okay.
that's right. And it has to be because, you know, a unit vector, multiplying something by a unit vector, well, a unit vector has a length of 1, you know. So if you have something that's 50 times a unit vector, the magnitude has to be 50. You can think of it as like multiplying 50 times 1. You know what I mean? Unit vectors never change that magnitude. Any other questions about this problem? Any other, are you going to ask questions the rest of the time?
Yeah, I have a
Yeah.
question. And I don't know if you guys, like, maybe the rest of the class, do you guys remember if we went over that problem 5 from the statics homework? It was the one that had, it was like.
Oh, with all the pulleys and stuff? I don't know if we've done it in class. Okay, let's do that one.
Oh, wait, no, sorry.
Not that one?
Yeah, not that one. I have it. It's all written over.
Okay.
It's the one that's like a 20 kilogram block on a 20 incline.
Okay. Okay. So it's a 20-degree incline. box has a mass of 20 kilograms and it's at rest on the incline. Its friction contact and there's a force of 50 newtons that way. And first it asks, calculate the force vector on the box by the incline. Second, it asks for the force applied to the incline by the box. And then third, it asks for normal and friction, like to break down this force on the box by the incline into a normal part and a friction part.
So this is kind of like a little bit separately because of the tension distance.
Is it the same or is it from?
Well, we're going to treat it differently because we're not going to break it up into a normal and a friction force until we get to part C. We treat friction contact just as an unknown force. So really it's easier than that. You don't have to deal with the unit vectors until you get to part C. So what are the normal and friction parts? Number 5, yeah. Okay, so first, free body diagram. There's the weight, 196.2. I guess I'm not very creative with those masses. And then there's the horizontal force of 50 newtons. And then there's the friction contact, which we're just going to treat as an unknown force. I'm going to write it as a force on the block by the incline.
Basically,
We
we don't know the direction, right?
don't know the direction, right? So we just have an unknown x component and an unknown y component. So Newton's second law says FBI, I'll break it up into components. Plus negative 50, 0. Plus 0, negative 196.2 is equal to zeros. And so the force on the block by the incline is equal to positive 50, positive 196.2. Part B, so this is part A. Part B then is easy because Newton's third law says FIB is just equal to negative FBI. So it's just equal to negative 50, negative 196.2. So if you're trying to figure out, if you're doing an engineering problem where you're trying to figure out how likely it is that that incline is going to break, and you need to know the loads that are being applied to it, this is the thought process you would use to know what loads are being applied to the incline. Okay, and then the last one. we have a force vector like this. Let me try to, so negative 50, negative 200. So it's basically like the vector is that way. Okay. And we want to break that up into a component that is perpendicular to the ramp. That's going to be the normal. And a component that's parallel to the ramp, that's going to be the friction, where these two are perpendicular. So the way to do that, if this is the vector force on the block by the incline, we want the projections yeah, this is FBI. Do I have it backwards? Yes. Yeah. Okay, we want the projections of FBI onto the green and red lines. To do that, we're going to take the dot product of the force on the block by the incline with unit vectors in those directions. Okay, so we need unit vectors in the green direction and the orange direction. So how are we going to do that? Here's our coordinate system. We know that this angle is 20 degrees. And we know that this angle is perpendicular to the red one. That red is in the same direction as the orange line there, and the purple is in the same direction as the green line. So we just need unit vectors representing those two things. So let's do the normal force first.
The red line is the incline.
Yeah. So theta is equal to 160 minus 90. So 70 degrees. And so the unit vector in the direction of that red line is cosine of 70 sine of 70, which is 0.342, 0.940. And now we're going to take FBI dotted with that unit vector. So that's so 50, 196.2 dotted with 0.342, 0.940. What do you get? 201.47 newtons. And that's the normal force. Well, if we would have gotten a negative, we would have just taken the absolute value, and that would have been the normal force.
Okay, so you're taking this big force in an x and y direction, and then you're dotting it with the unit vector specifically of the normal force?
Right, specifically in the direction that, like, to get a projection onto a line, you take a unit vector in one of the two directions representing that line, and then dot the vector with that, and it gives you the projection. So what we figured out is, well, we figured out this green here. I only have one regret in my life, and that's that I didn't make this orange to match this orange, and this green to match this green. Okay, and now we're going to do the same thing with the friction force. So now I want a unit vector in the direction of that red vector, or the opposite would be fine too. We're just going to take absolute values in the end anyways. So theta is equal to 160. So the unit vector is cosine and sine of 160. Which is negative 0.940, positive 0.342. 180 to get there, and then backtrack 20. And so the force of friction is the absolute value of, what do we get for 50, 196, dotted with negative 0.940, positive 0.342. And what's the dot product there? 20.12? Yeah, the normal and the friction force that we want are we just want the magnitudes of those. And so whatever, depending on which way, like if I would have happened to choose, instead of this purple, I would have happened to choose my unit vector this way, we would have gotten a negative 201.47. Just throw out that negative. We don't care about that. And then this one, if I would have chosen this one instead, we would have gotten the negative value for the friction force. We don't care about that. We just want the magnitude. Any other questions about that one? Down?
So, in the absolute value of the unit vector, you multiply by the absolute value of the unit vector, or by the magnitude?
Ask that again.
Oh, so you multiply by the absolute value of the unit vector, or?
No, just if it asks for the normal force and the friction force, we don't care about plus and minus on that. So just report the positive value, that's all I mean. But the way to calculate it is take the dot product of that unit vector with the force. That's a way you can always calculate a projection of one vector onto a direction. Dot product of a unit vector with the original vector.
So basically, if you multiply, you can't multiply, you have to take the dot product.
Dot product, right. You know, vectors, there's no such thing as just multiplying. You have to choose what kind of multiplication you want. It could either be cross product or dot product, and we want dot in this case. Yep.
It might sound trivial, but dot product again, that's when you just add the top, or you multiply the top row and then you add the multiplication
So
of the bottom row.
it would be 50 times negative 0.94 plus 196.2
Yeah, okay.
times 0.342. And if you're lucky, I don't think you're lucky, but if you have a TI-89, then
Not lucky.
then you just call it, then you just go dot P, put those two vectors in, and you don't have to think about it any more than that.
Okay.
Then you're just like a manager. You'd like delegate responsibility to your calculator. You don't need to micromanage. Any other questions about this one? Yep.
So we did the dot product, they asked for and at the magnitude, right? The scalar of, because that's why we did the dot product.
Right.
Okay. What if they ask for the vector? We already found the vector by doing like if they ask the vector component.
If it asks for the vector components?
Yeah.
Well, we had that originally,
Oh,
but you mean if it asks for it in a different coordinate system or something?
So we.
What we started with was the vector components.
Oh, we started with it.
Right.
We first found the vector component.
Yeah, that's right.
We transfer it when you found it.
And then we found projections of that vector onto two other directions.
Oh, okay.
I have to be honest, I think that's something that you've seen before, probably in a class quickly. I wanted you to see it again, but I'm not going to put something like that on the test, that projection thing. But it is a useful thing to, slowly be wrapping your heads around as you get more familiar with vectors. Yep.
Can you go through part C again?
Part C? Yeah. Actually, let's not. So that's not going to be on the test. Let's just do that. And then if you look at it and have questions about it, I'd be happy to answer questions about it later. But that's supposed to be just gentle brain expansion. But that's not going to be on the test.
About something to do with like cross product of example, like vector
Uh-huh.
cross product.
Yeah, so mainly what we've done with cross products so far, until we get to rigid body statics, is just using cross products to figure out perpendicular.
Yeah.
So
It's like the direction and which like the first example.
okay, so the cross product U cross V gives a vector that's perpendicular to U and perpendicular to V. That's one of the most useful things about the cross product. And the way it works intuitively is any vectors U and V define a plane. So say this is U and this is V. those vectors lie in a plane together. And the cross product is a vector that's perpendicular to that plane. So there are two possibilities for vectors perpendicular to that plane. One that way, and one that way. The cross product follows the right-hand rule. So if you're taking U cross V, you put those two tail to tail, your hand goes through the rotation, your thumb tells you the direction of the cross product. So, for example, what's a unit vector perpendicular to both 6, 5, 1 and negative 2, 0, 4? Well, a vector that's perpendicular to both of those you get just by taking the cross product. So I'll go 6, 5, 1 crossed with negative 2, 0, 4. So that's 20, 24, 26, negative 26. And then 10. Is that right? Maybe.
We can use our calculators on that test.
Yeah, right. Yeah, you just plug it into your calculator. And if your calculator doesn't have cross product, dot product too, if it doesn't have those built in, you probably should just make a program that does it. And come to office hours and I'll help you do that. But the formulas will be given on the test. You can just punch it in. If your calculator does it, you don't even have to do that much. Okay, so that's a vector that's perpendicular to both of these, 6, 5, 1, and negative 2, 0, 4. But it's not a unit vector. So to make a unit vector in that direction, calculate the magnitude. So the magnitude of this is 20 squared plus 26 squared plus 10 squared square root. What is it? 34.29. And then the unit vector is 20 over 34.29, negative 26 over 34.29, and 10 over 34.29. Do you have components for that? Okay. 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 And so that's a unit vector perpendicular to both of those two original vectors. If you wanted a second unit vector perpendicular to both of those original vectors, how would you do it? It's just going to be the opposite of that, because you can think of it as what we calculated was, we calculated the one that follows the right-hand rule. And if you take the opposite of every component, it gives you the one that's in the opposite direction. if you took the magnitude of this vector, what would you get? 1, yep. Any questions about that problem? Okay. The cross product thing, yeah. Well, this is how I learned it. If you go, so 651 negative 204. 651 negative 204. And think of taking the determinant. So that's I times this, or you can think of it as to get the stuff that goes in I, you cross all this stuff out and take the determinant. So that's 20 minus 0. And then minus j times cross this stuff out and take the determinant. 6 times 4 minus negative 2 times 1. So that's 24 minus negative 2. And then plus k times 6 times 0 minus negative 10. And so that's 20, negative 26, positive 10. But I recommend that you come up with some system with your calculator so you don't have to use that formula, you know. It's just wasted time that you could be eating ice cream or whatever.
For the direction, you go like let's say u plus v, you go from u, you put it down to v, and then
Right.
discount for each value.
That's right. Yep. Any other questions? 5 minutes left? Okay. Test Thursday.